Hello everyone, I am Dr. Avradip, Assistant Professor of Physics working in Nanajol Raj College. And today the topic we will be going to discuss is about gravitation, which is included in the core course C2 of first semester honors syllabus in physics. So let's start with the definition and effects of what is known as gravitation. We all know a little bit about gravitation during our school days and also in the plus 2 courses. So gravitation is basically one of the four fundamental forces, gravitation, and it is the theory of gravitation is actually pretty old. It's very old theory, and which was discovered during the 16th century, and it was Sir Isaac Newton who first depicted or formulated the way the gravitation we see the formula today. So let's now discuss about what is the Newton's laws of gravitation. So what Sir Isaac Newton said is that any two objects in the universe, being it a very small object or a very large object like a planet or even a bigger than that, like they all feel attraction due to the gravitation. So any two objects, the only condition between the attraction of gravitation is that both of them, they have to have masses, and if they have mass, they will attract each other. So Newton's laws of gravitation, first of all, it says that the force of attraction between any two masses, particularly point objects of the magnitude of the force is directly proportional to the product of the two masses of those two objects, and it is inversely proportional, the magnitude of the force is inversely proportional to the square of the distance between those two objects, as simple as that. And this is probably which we have already seen and or studied during our plus 2 course. So let's discuss this in a little bit mathematical form. So let's say there are two such point objects which I have shown in these two red dots. The first one is having a mass, say Ma, the second one is having a mass, say Mb. Then Newton's laws of gravitation basically says that the force of attraction between both of them, the magnitude, so there are actually two forces which will come into play. I am writing both of them. The force which will be acting on the first particle, the particle which is written as Ma, which is having a mass Ma, I will say the force of attraction which is affected on A is Fa, and it is because of B, so I am writing the force as Fab. And the force which will be affecting the mass Mb, that I will write the force as Fb, and it is due to A, so that's why this force is Fba. So what Newton's laws of gravitation says that these two forces, first of all, their magnitudes are first of all equal, and they have to be the magnitudes, because it's again the Newton's third law of motion, which says that each and every action has its own and opposite reaction. That says, but then now comes the magnitude. So the magnitude of both of them is basically directly proportional to the product of these two masses, and also it is, if we now join these two objects by a straight line, and if we call the distance between them as RAB or RBA, whatever, because both of them are basically the same thing, so it's RAB or RB's whole square. So that's what Newton's laws of motion, laws of gravitation tells us. So now there is a proportionality constant which has come in front. So in order to remove that proportionality constant, what we will be doing is very simple. It's the simple law of variation. So we'll introduce a constant which will definitely not be dependent on the mass Ma, which will not be dependent on the mass Mb, and definitely not on the distance between those two masses, point objects. Now question is, what is G? G is basically, now we all know that it's an universal constant. It's known as the gravitational constant or universal gravitational constant, or even Newtonian constant by the name of Sir Isaac Newton, and it basically gives us the idea of how strong is the force of attraction between these two masses and these two particles. Now we'll be interested to know what exactly is the value of this G is, and also the what is the unit of this constant is. So as we know that the value of g, it's because it's an universal constant, so it doesn't matter whether you measure it on the surface of the earth, or you go in moon or in sun or any other planet or whatever, the value of g remains the same, and the value of the g is more or less quoted as 6.673 into 10 to the power of minus 11 meter cube kg inverse and second to the power minus 2. Now the thing is, it's very difficult to actually accurately measure the gravitational constant due to the fact that among all the four fundamental forces which I just talked about, gravitation is the weakest one. The strongest one is the strong force, the next one is the electromagnetic force or the Coulombic force, the third one being the weak force, and the weakest of all those forces is the gravitation. It's very difficult to measure that, and that's why it becomes very difficult to measure the gravitational constant accurately. But more or less we take this value as the more or less it's the accepted value of gravitational constant. Now comes the vectorial notation. How exactly do we express this particular force? Because as we have already seen, this force of attraction, there are two such forces. One force is acting on the particle, the mass ma, the second one which is acting on the mass mb. So now comes the direction of that. So it's basically very clear that the force FAB, which is acting on the particle ma, and due to the particle b, or which is having a mass b, will be FAB, and it will be directed towards this side because it's being attracted, the mass ma is being attracted towards the mass mb. And similar way, the force FBA, the direction of this force will be pointing towards the mass like this. So in a vectorial notation, what we'll be doing is basically, now we have to write the position vector. Say for example, if we try to express the position of the mass mb with respect to the mass ma, what we'll be writing, will express the position of this particular vector in of this particular particle as RBA, like this. It's the position of the particle B with respect to A. So the force which will be acting on this particular mass, we have seen that it's acting exactly opposite to the position vector of that. So what we'll be doing, introducing a unit vector of this position which will be pointing out from this particular particle. So that will be writing as RBA with a hat or cap sign over there. So now it becomes very easy for us to write the force as FBA. Now first write the magnitude. It's GMAMB divided by RBA squared, that we have already written. Now comes the magnitude. Now we have to introduce the unit vector because we have to write the force in terms of that. So when we write RBA hat, now we see, using the vectorial notation, the direction of this vector and this vector is actually the opposite. So we'll balance that by introducing this minus sign. Now everything is clear, because this is the magnitude, this vector is pointing out, but the actual force is pointing in because it's acting in this side. So we'll balance that by introducing a minus sign. And the same happens with, if we try to write this particular the force acting on this particular particle. So it will become FAB will be, again, it's minus GMAMB divided by RBA square. This is basically the magnitude, so it doesn't matter whether if we write RAB or RBA, and this will becomes RAB. And as we have already seen, by using the vectorial notation, if we try to write the vectorial sum of these two forces, they will be basically 0. So FAB plus FBA, it is very easy to establish that they will become 0, because if one is considered as the action, the other one is reaction. Okay, so now let's go into the deep detail of the gravitation and its other so we just talked about the gravitational forces, but there are a few more terms which we need to learn. So I'll write them down in the board. So the few terms which are going to be very, very crucial is gravitational field gravitational field, we will write the symbol as small f with a vectorial sign on top of that. So there will be another term, it's known as gravitational potential energy. Gravitational potential energy written as U, will use a suffix as G, just to keep in mind that this is coming from the gravitational force. And the next one will be gravitational potential, which we will be writing as V, again as suffix as G. Suffix G, just to keep in mind that it's coming from the gravitational force. So out of these three parameters, three well-known parameters or variables, the first one is a vector. The second, the last two, they are scalar quantities. So let's try to define or explain what are these variables. So gravitational field is very simple. It's basically, before we actually talk about gravitational field, we have to understand, in order to have the effect of gravitation, we actually discriminate between the two particles. Actually, what we talked about here is basically something called a source object or a source mass. And there is something, or source object, you can say as source object, and then something which we call as test mass. Now what is that? Test mass and source mass. So we'll keep on using the capital letter for the mass, the capital M for the source mass, and the small m for the test mass. It is something that the source mass is something which will be considered as something which was already present there, because the source mass was present there, it had created the gravitational environment around that, and then we will be considering that a test mass has been taken in the environment of the source mass, or the gravitational environment which has been created by the source mass, and now we will be looking into what is exactly the forces and other things which are being experienced by the test mass. So test mass is something which we'll introduce later. The thing which will be already present there in the system will be the source mass. Say for example, the sun in the planetary system, in the solar system, sun is already present there, and now sun is basically will be considered as the source mass. And if we try to consider the effect which is experienced by Earth or other planets, they will be considered as the test mass. So we will introduce the test mass in the environment of the source mass. So what is happening here? So by the law of gravitation, we have seen that, say for example, if this is a source mass, for the timing let's consider just only point objects. Source mass is also a point object and test mass is also a point object. Source mass is like pointed here, it has a mass m. Now if we take the test mass which is having a mass of small m in a distance of, say for example, we'll call the position of this particular test mass as r with a vectorial sign on top of that. So this is the position of the test mass with respect to the source mass. Source mass is the origin. So now we will ask the question naturally, what is the force of attraction which is affecting the test mass? The force of attraction is due to the gravitation. That is very simple to calculate. We have already seen that. So the unit vector is pointing towards like this side, but the force of attraction will be pointing towards the capital M, the source mass. So the force of attraction which is acting on the test mass will be very simple. So the force of attraction is a function of r, the position here, and it can be written as we have seen, minus g capital M small m by r square, and then r vector in front on top of that. So r cap on top of that. So this will be the force of attraction of gravitation which will be attracting the test mass of small m towards the source mass of capital M. This we have already seen. I have rewritten that. Now the question is, what is gravitational field? Gravitational field is defined basically in a very simple way. I'll try to explain that. It's the same thing. It's the force of attraction, but just only when the test mass is considered to be a unit mass. Which means, if we consider the test mass as 1, the force of attraction being experienced by that unit test mass will be considered as the gravitational field at that particular point due to this particular source mass, capital M. So basically in this expression, if we put small m is equal to 1, what we get is basically the gravitational field at that particular point, which will be gm by r square with a cap on top of that, gm by r square. This is basically the gravitational field of the due to this particular source mass at this particular point, which is nothing but the force of attraction experienced by a unit test mass. So if we had taken the unit mass and kept that mass over here, the force of attraction was this only. So that's why most of the time you will be seeing that our main concentration is mostly on the gravitational field. We generally don't try to calculate what is the gravitational force over there, because if we know the gravitational field at some point, it becomes very easy to calculate the gravitational force, because if you compare these two particular equation, you will be seeing that at a specific point the gravitational force will be nothing but it is the product of the mass, test mass, and the gravitational field over there. So test mass is in your hand. So if you just somehow calculate the gravitational field due to the source mass at some point, all you need to do is just to multiply that field with the test mass, and you will all get the force which will be experienced by the test mass. As simple as that. So that is called as a gravitational field, and as you can see, gravitational field for a test mass, a source mass, is actually dependent on r and is actually inversely proportional to the square of the distance of the r. So as you go far and far from the source mass, the force of attraction, the magnitude of the force of attraction actually goes down and eventually becomes 0 as r tends to infinity. It means when the test mass is actually sitting almost infinite distance from this source mass, it doesn't feel any force of gravitation. So in that sense, actually we call that the range of the gravitation is actually, it's a long range force, because it can go up to infinity theoretically. Okay, so if we try to plot the nature of the space dependence of the gravitational field for a point source mass m, then the graph will somehow look like this. So it's the field will be so I'll try to plot the magnitude of that, and because it's negative, that's why I have the force. Actually I can, if it's a magnitude, it will be positive, so there is no problem if I plot it like that. I'm just plotting the magnitude, so basically it will be positive. So I'm just trying to plot the magnitude, not the overall force. So it will be something like this. In the x-axis I am plotting the distance, in the y-axis I am plotting the gravitational field due to a point source object having a mass m. So it will be something like this, because at r equals to 0, this function blows up, goes like this asymptotically. So it goes down as 1 by r square, the magnitude of that, and eventually becomes 0 at r tends to infinity. This will be the nature of that, the gravitational field. Now comes what is known as gravitational, the other two parameters, gravitational potential and gravitational potential energy. So let me introduce that one in front of you. So gravitational potential energy, I'll write this as UG. So in order to introduce the gravitational potential energy, I have to consider the work done by the gravitational force. So the way it has been defined, the gravitational potential energy. Question is, so in front of the source mass, so the source mass is creating the gravitational environment, as we have seen, it's creating the gravitational field and other things. So now a test mass has been kept in front of that. The question is, it's experiencing a force of attraction. So question is, now if it is situated at a particular point, say for example the position is A, and it's experiencing a force, and the force is force of gravitation. Now in that force, if we take this particle from a position A to another position B, somewhere here, if we take this particle from here to here, naturally the force of attraction has to do some work that we know already. The work done needs to be done, and the way we will be calculating the work done is basically the way we have seen. Work done is always calculated as F dot dr for a infinitesimal displacement dr, and if we try to consider it for a longer length, then what we have to do, we have to just do the line integral over that. So because F dot dr basically gives you the infinitesimal work done dw, and the total work done is calculated as integral F dot dr, where we have to choose the proper limits from the initial position to the final position. Now that's the way we need to calculate the the work done by the gravitational force. Now the question naturally arises, what happens if we try to take this particular test mass from the infinite distance to a final point, say R. Okay, what happens then? Now that's the question which we need to answer. What happens? How much work done we need to do? So that's very easy to calculate for a pointed source object. The source object having a mass, say m. Now let's say it's situated at a distance at say x. This test mass is situated at a distance x, and we can infinitesimally displace this particle as dx, so that dx can be written as dx in the magnitude and the corresponding unit vector like that. And we know that the force of attraction which is experiencing by this particular test mass at that particular point is nothing but F will be minus g mm by x square into x cap and the minus sign in front. So now if we try to displace this particle from by a smaller amount of dx, what is the total work done, the infinitesimal total work done? That will be dw, and nothing but it's F dot dx, as simple as that. And if we calculate the dot product, it will come out to be, because this x dot x will become 1, there is a minus sign in front which will it will pick up, so it will becomes minus g mm dx over x square, and there is a minus sign in front. This will be the infinitesimal work done by the gravitational force. Now question is, what happens now if we take the initial point is at infinity and the final point is somewhere at a point R. Say for example, with the final point why we have taken this particle is somewhere here. The position is given and the initial point is somewhere in the infinity. What will be the total work done? So total work done, now we have to just integrate this expression with the proper limits. So the total work done W will be integration, so minus g mm dx by x square, and the limit will be from infinity to the R. And now because there is no vector, so because it will consider only the magnitude of R, so it is not dependent on the vector R, it's only dependent on the magnitude. So if we calculate this one, what will come? So minus g mm will go in front. We have integration infinity to R, it's dx by x square. So what will happen? Dx by x square, if we integrate that, it will be minus 1 by x, the minus and minus will cancel. So what we are remaining thing which we are having with is basically 1 by x, it's from infinity to R. If we take the proper limits, it's 1 by R, and if we put infinity, it will become 0. So it's basically g mm by R. The work done in taking the particle from infinity to the distance R with the gravitational force, this is the work done. Now the gravitational potential energy is defined by the negative of the work done in taking the particle from the infinite distance to that point R. So gravitational potential energy at that point is nothing but will be negative of that. That's how the gravitational potential energy is defined. So Ug is defined as minus of W. So in this particular case, if we try to calculate what is the gravitational potential energy due to that source object of capital M, so it will be nothing but, so the work done came out to be positive. So eventually the gravitational potential energy will be negative. So it will become minus Gmm by r. And as we can see, it's dependent only on the magnitude of r, and because it's a scalar, there is no vector sign. One important point to note that the sign is minus, so gravitational potential energy is actually negative. This is a very important conclusion which we can recheck, is because the force of attraction is attractive in nature. Interaction is attractive in nature. That is interpreted or eventually is reflected as the gravitational potential energy as negative one. If we had a force of interaction as repulsive forces, then we could have got the gravitational potential energy as positive. But the gravitational interaction is always attractive in nature, so always we'll be getting the potential energy as negative. For example, the Coulombic interaction, we know the formula is similar to that of the gravitation, but in that particular case we have force of attraction and force of repulsion as well. If the force is attractive in nature, we'll get the potential energy as negative. If the interaction is repulsive in nature, then we will get the potential energy as positive. So here the negative sign clearly indicates that the total force of interaction is attractive, first of all. And the second thing is that the magnitude of the potential energy goes as 1 by r. So the force of attraction was going as 1 over r square, the potential energy goes as 1 over r. So if we try to plot the magnitude of that, it will not fall so sharp as the force, because it goes as 1 by r square. Here it will go as 1 by r, but eventually at r becomes infinity, this gravitational potential energy will become 0. So the more it will come closer to the source mass, the more and more negative the potential energy will become. The magnitude will increase, but there is a minus sign in front, so it will become more and more negative. But the farther it will go away, it will keep on losing its magnitude, and eventually at infinite distance will become 0. Now question is, what is the gravitational potential then? Gravitational potential is basically, it's the similar kind of relation what we have seen in force and field. It's the same thing in between potential energy and potential. So instead of a test mass m, if we had kept a test mass having a unit mass, the gravitational potential energy experienced by that unit mass, we would have called that as gravitational potential. So in this expression, if we just keep m equals to 1, what we'll get as gravitational potential, and that is known as written as Vg. So gravitational potential is defined as the gravitational potential energy experienced by a unit mass kept at that particular point. So for a test pointed mass of having magnitude capital M, the gravitational potential is calculated as minus Gm by r, as simple as that, because we have to just put small m equals to 1. So all we need to calculate the gravitational potential, and if we want to calculate the gravitational potential energy, what we have to do, we have to just multiply this expression with the mass of the test mass, and all we get is the total gravitational energy. So again, just like our main focus was on gravitational field instead of the gravitational force, in this case also our main focus always will be with the gravitational potential instead of the gravitational potential energy. That's for this particular discussion and lecture. Thank you.